All right, so let's do an example. I would like you to give the electron configuration and the bond order for three different species, three different diatomics. F2, the F2 plus cation, and the F2 minus anion. Then, once you've calculated the bond order, you can figure out which of these species has the strongest bond. So the way that we do this is by going back to our table here and figuring out which order we want for the F2 molecule. So F2 is over here, and the order of molecular orbitals is given here. So I've copied that down 3 times to make molecular orbital diagrams for all 3 of these species: the F2 neutral molecule, the F2 plus cation, and the F2 minus anion over here. So we have to figure out how many valence electrons each of these species is going to have, and then we can just fill up the molecular orbital diagrams very easily. So for F2, each fluorine has 7 valence electrons, so we're going to have 14 valence electrons total. For F2 plus, we're simply subtracting one of those electrons to get the plus charge. And for F2 minus, we're adding an additional electron, so we have 15 valence electrons that we need to fill up the MO diagrams with. So now we can take those 14 electrons and start filling up the molecular orbital diagram using the Aufbau principle and Hund's rule, starting with the lowest energy MO. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so here all of the electrons are paired up. For the F2 plus, we're just going to be missing one of the electrons. 11, 12, 13. So there we have one electron that's unpaired. Finally, for the F2 minus, we're going to have 15 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so right away we can see that the F2 molecule is going to be diamagnetic, whereas the F2 plus and F2 minus are both going to be paramagnetic because they have unpaired electrons in their MOs. Diamagnetic means that the F2 molecule has all of its electrons completely paired up. Now, when you're asked a question like this to give the electron configuration, you don't actually have to draw out the whole diagram if you don't want to. There's a shorthand that you can use to give the electron configuration quickly. So I'll show you how that shorthand works because it will save you time as you start getting used to doing those things. So you write the molecular orbital designation, and then you show how many electrons are in each orbital using a superscript. So here, this one would have the 2 electrons in it, as you can see there. So I can do that for each of the MOs. Sigma star 2s has 2 electrons in it. Sigma 2p has 2 electrons in it. Pi 2p has 4 electrons in it. And pi star 2p has 4 electrons in it as well. Okay, so this is just the shorthand to show this MO diagram kind of just all in one line. Now I can also use the shorthand to show the electron configuration for the ion, sigma 2s 2, sigma star 2s 2, sigma 2p 2, pi 2p 4. And now this one's lost one of the electrons compared with the one above it, so I'm going to have 3 electrons in the pi star 2p. Finally, the shorthand for the F2 minus anion would just be sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, pi star 2p4, and now we need one more electron to give that negative charge on the ion. So that's going to go into sigma star 2p. So I just have one electron there. So these would be the electron configurations for all three of those species. Now, to calculate the bond order, I want to subtract the number of bonding electrons, so the number of electrons in bonding orbitals, minus the number of anti-bonding electrons, the number of electrons in anti-bonding orbitals, and then divide that number by 2. So if I do that for each of these species, for F2, there are, let's see, 2, 4, 8 bonding electrons minus 6 anti-bonding electrons divided by 2. So what's 8 minus 6? 8 minus 6 is 2, divided by 2 is going to be 1. So I have a bond order of 1 for F2. For F2 plus, the F2 plus has just one fewer anti-bonding electron. So that's going to be 8 minus 5 divided by 2. So that's going to be equal to 3/2 or 1.5. The F2 minus anion, by contrast, has one extra anti-bonding electron. So its bond order is going to be 8 minus 7 divided by 2. And that's going to be equal to 1/2 or 0.5. So when you are asked which is the strongest bond in the question, the strongest bond is going to be the one that has the highest bond order. So the strongest bond is going to be F2 plus because the bond order is 1.5, and that's the highest bond order of all three of these